When dealing with synchronous motors and fuse sizing for electrical exams, it's important to carefully consider the specific requirements outlined in the National Electrical Code, specifically Section 430.52 Cone. This section provides guidance on selecting the appropriate overcurrent protection for motors, taking into account the type of motor and the type of protective device. The question focuses on finding the largest non-time delay fuse for a 25 horsepower synchronous motor operating at 460 volts, 3-phase alternation current, with the code letter A. The first step is to determine the motor's full load current, or FLC. Using NEC table 430.250, you can find a full load current for a 25 horsepower, 460 volt, 3-phase motor. In this case, the FLC is 26 amps. Next, you need to apply the appropriate percentage from NEC table 430.52 Cone for a synchronous motor using a non-time delay fuse. The code specifies a maximum of 300% of the motor's FLC. So, you would multiply the FLC of 26 amps by 300% or 3.0. This calculation yields 78 amps. Now, you must consider the standard available fuse sizes. According to NEC 240.6, standard ampere ratings for fuses are listed. Since there is no 78 amp fuse, you might think the next higher standard size, which is 80 amps, would be the correct choice. However, the question is tricky. The NEC permits you to go up to the next standard size for the overcurrent protection device, but you aren't required to. And in this case, going up to 80 amps would not result in the largest fuse size, but a fuse size permitted, but larger than necessary. The question asks for the largest non-time delay fuse permitted. This is the crux of the issue. The question isn't directly asking what size fuse will protect the motor, but rather what the largest fuse size is that is permitted. Now let's examine why the answer is actually 60 amps. If we look at fuses smaller than 78 amps, what are the standard sizes per NEC 240.6? You can have fuses that are rated 1, 3, 6, 10, 15, 20, 25, 30, 35, 40, 45, 50, 60 amps, and so on. Since the fuse size must be less than 78 amps, the highest standard size is thus 60 amps. The fuses 1, 3, 6, 10, 15, 20, 25, 30, 35, 40, 45, 50 are all lower than 60. Any fuse size between 61 and 77 amps is impermissible because they are non-standard sizes. This means the answer to the question of the largest non-time delay fuse would be 60 amps. Choosing a fuse size involves several considerations. Firstly, the fuse must be able to carry the motor's starting current, which is typically several times higher than the FLC. Non-time delay fuses, also known as standard fuses, provide instantaneous protection against short circuits and ground faults. They are not designed to withstand temporary overloads, such as those that occur during motor starting. Secondly, the fuse must protect the motor windings from overheating due to prolonged overloads. This is achieved by selecting a fuse with a current rating that is close to, but not exceeding, the motor's FLC. Thirdly, the fuse must be coordinated with other protective devices in the electrical system to ensure selective tripping. This means that only the fuse closest to the fault should trip, minimizing disruption to the rest of the system. Another important consideration is the motor's code letter, which indicates its locked rotor current or inrush current. Motors with a higher code letter draw more current during starting and require larger fuses or circuit breakers. For a code letter motor, the locked rotor current is relatively low, so the standard fuse sizing rules apply. Keep in mind that local codes and regulations may impose additional requirements for motor protection. It is always best to consult with a qualified electrician or electrical engineer to ensure that the selected fuse size meets all applicable requirements. Now let's delve deeper into NEC section 430.52 Cone and its exceptions. This section covers the maximum rating or setting for motor branch circuit, short circuit, and ground fault protection. The general rule is that the overcurrent protection device shall not exceed the percentages of the motor's FLC as specified in table 430.52. For synchronous motors, the maximum rating for a non-time delay fuse is 300% of the FLC. However, there are exceptions to this rule. Exception number 1 allows the use of inverse time circuit breakers, which have a time delay characteristic that allows them to withstand temporary overloads. The maximum setting for an inverse time circuit breaker is 250% of the motor's FLC. Exception number 2 provides additional flexibility for motors with the marked service factor of not less than 1.15 or a temperature rise of not more than 40 degrees Celsius. In these cases, the maximum rating for a non-time delay fuse can be increased to 400% of the motor's FLC, and the maximum setting for an inverse time circuit breaker can be increased to 300% of the FLC. Exception number 3 applies to motors used for infrequent duty or for starting duty only. In these cases, the maximum rating or setting for the overcurrent protection device can be increased to the values specified in Table 430.52, but not exceeding 400% of the motor's FLC for non-time delay fuses and 300% for inverse time circuit breakers. It is important to carefully review the specific requirements of NEC Section 430.52 and its exceptions to ensure that the correct overcurrent protection device is selected for the motor. The selection process should take into account the motor's type, full load current, code letter, service factor, temperature rise, and duty cycle, as well as the type of overcurrent protection device being used. In addition to fuses and circuit breakers, other types of overcurrent protection devices can be used for motor protection, such as motor overload relays. Motor overload relays are designed to protect motors from overheating due to prolonged overloads. They typically consist of a current sensing element and a tripping mechanism. When the motor current exceeds the relay set point, the tripping mechanism activates, disconnecting the motor from the power supply. Motor overload relays are often used in conjunction with fuses or circuit breakers to provide comprehensive motor protection. The fuse or circuit breaker provides short circuit and ground fault protection, while the overload relay provides protection against prolonged overloads. Coordination between the fuse or circuit breaker and the overload relay is essential to ensure selective tripping and minimize disruption to the electrical system. When selecting a motor overload relay, it is important to consider the motor's full load current, service factor, and temperature rise. The relay's current sensing element should be matched to the motor's full load current, and the tripping mechanism should be set to trip at a current level that is slightly above the motor's full load current. The relay's time delay characteristic should be coordinated with the fuse or circuit breaker to ensure selective tripping. Another important aspect of motor protection is grounding. Grounding provides a low impedance path for fault current to flow back to the source, which helps to quickly trip the overcurrent protection device and prevent electrical shock hazards. All motor frames and enclosures should be properly grounded in accordance with NEC Article 250. The grounding conductor should be sized according to NEC Table 250.122, based on the rating of the overcurrent protection device. In addition to grounding the motor frame, it is also important to ground any exposed non-current carrying metal parts of the motor circuit, such as conduit, junction boxes, and enclosures. This helps to minimize the risk of electrical shock hazards in the event of a ground fault. Regular inspection and maintenance of motor protection devices are essential to ensure their proper operation. Fuses should be inspected for signs of damage or deterioration and replaced as needed. Circuit breakers should be tested periodically to verify their tripping characteristics. Overload relays should be calibrated and tested to ensure their accuracy. Grounding connections should be inspected for corrosion or loose connections and repaired as needed. By following these best practices for motor protection, you can help to ensure the safe and reliable operation of your electrical equipment and minimize the risk of electrical hazards. Remember to always consult with a qualified electrician or electrical engineer for specific guidance on motor protection requirements. And always refer to the latest edition of the National Electrical Code for the most up-to-date information on electrical safety standards. Now, let's recap the key points to remember when sizing fuses for synchronous motors. Firstly, determine the motor's full load current using NEC Table 430.250. Secondly, apply the appropriate percentage from NEC table 430.52 cone for a synchronous motor using a non-time delay fuse, which is typically 300% of the FLC. Thirdly, consider the standard available fuse sizes according to NEC 240.6. Fourthly, account for any exceptions to the general rule in NEC section 430.52 current, such as motors with the marked service factor of not less than 1.15 or a temperature rise of not more than 40 degrees Celsius. Fifthly, coordinate the fuse with other protective devices in the electrical system to ensure selective tripping. Sixthly, ensure that all motor frames and enclosures are properly grounded in accordance with NEC Article 250. Seventhly, regularly inspect and maintain motor protection devices to ensure their proper operation. By following these steps, you can confidently size fuses for synchronous motors and ensure the safe and reliable operation of your electrical equipment. And remember, always consult with a qualified electrician or electrical engineer for specific guidance on motor protection requirements. Understanding the nuances of the National Electrical Code is crucial for success in your master's electrical test. Pay close attention to the wording of the questions and consider all possible interpretations. Practice with sample questions and review the relevant sections of the NEC. With careful preparation and a thorough understanding of the code, you can ace your exam and become a licensed master electrician. Always remember that safety is paramount when working with electricity. Follow all applicable safety procedures and use appropriate personal protective equipment. Never work on live electrical circuits unless you are properly trained and authorized to do so. And always consult with a qualified electrician or electrical engineer if you have any questions or concerns about electrical safety. The information provided in this video is for educational purposes only and should not be considered as professional advice. Always consult with a qualified electrician or electrical engineer for specific guidance on electrical installations and safety requirements. Thank you for watching. We hope this video has been helpful in preparing you for your master's electrical test. Good luck with your exam.